This is the ECE 3211 final project for John Nguyen, Garrett Soler, and Justin Niezrecki. Our final project was to create a solar inverter. The PCB that we designed consisted of a DC input of 12 volts to simulate a solar panel, and showcase boost conversion and an inverter for DC to DC step-up voltage and DC to AC conversion. Within this project, our goal was to use the power from a solar panel to light up an AC LED light bulb. However, instead of using a solar panel, which would have required a complex closed-loop control system to keep a consistent output current, we used a DC power source to give the input voltage that we would have received with our solar panel. One problem that we found with our PCB was a design flaw within our boost converter. When following the boost conversion design from Lab 7, we integrated the wrong chip, the IR2117, instead of the IR2127. This integration of the gate driver for the boost converter would have been with this circuit shown here. Instead, we used a different circuit implementation with the 2117 chip. For this reason, the boost converter portion of the PCB did not work. John will be showcasing the inverter portion of our project using a DC power supply.
So this is our PCB layout that we designed. On the left half is the boost converter, and on the right half is the inverter. However, the boost converter does not work, and that was explained beforehand. So from this cable that you see is it's providing ground to the PCB. This cable provides the 15 volts to power the chip, and this cable also provides 15 volts for the inverter. And our output, we should expect roughly from between 20 to 25 VAC. And Garrett's going to handle the power supply part.
Alright, so now if we turn the power on to the PCB, we see that it turns on. So yeah, we're supplying 15 volts. And if we look at the oscilloscope up here, this is our output voltage. And we see, if you look right over here, you get a peak-to-peak of 20.4, which is a little lower than the expected value of 25 volts peak-to-peak, but it's still within a reasonable range.
Lastly, we wanted to showcase the problems that we experienced along the way and the improvements that we can make in the future if we were to do a PCB design on this project again.
So, as you guys can hear, the gate driver is giving off a frequency of sound that we can hear. So the reason that it's doing that is because the resistor value and the capacitor value that we chose are too high, which creates a frequency that's too low. And when we have such a low frequency for the gate driver, this creates that sound. Okay.
For future reference, to improve our PCB layout design, we these connector hole sizes are too large. We would need to decrease their size. And over here, as you can, this is the gate driver circuit for the boost converter that we wanted to go with, but instead we ended up with the one on the PCB layout, and that one obviously did not work. This, however, should give us the proper result, simulation result. And on this side, what Garrett was saying earlier, these two components, their values are way too high, so that's why the switching frequency was way too low, so that's why you guys hear the blaring, ringing sound.
In conclusion, the inverter portion of our PCB worked, but unfortunately not the boost converter. This was definitely a fun project with a lot for us to learn, and thank you for a fantastic semester.